This lesson is about specific latent heat. By the end of this lesson you should be able to explain what is meant by latent heat. You should also be able to describe when a change of state occurs that it's the change in the energy stored but not the temperature, and also be able to perform calculations involving specific latent heat, and for those of you doing the higher paper, be able to link those specific latent heat equation to the specific heat capacity equation. So before we start, pause the video and have a go at these two questions. So you should have remembered from a previous lesson that the difference between heat and temperature is that heat is the total amount of kinetic energy in a material, and that temperature is the average kinetic energy of a material. And the specific heat capacity equation is the energy needed to change the temperature of 1 kilogram of a material by 1 degree. So the equation itself is the energy equals the mass times the specific heat capacity of that material times the change in temperature. Whenever there's a change of state of any material, then energy is inputted into that material in order to change it from a solid to a liquid or a liquid to a gas. So when a material is being heated, the heat energy that's put into that material will rise the temperature until it gets to the point where it's actually changing state. So in the case of a solid to a liquid, when it's melting, as it's melting, all of the heat energy that's being transferred is actually being used to weaken the bonds instead of being used to raise the temperature. So during that period of time there is no raise in temperature. And again, when a liquid is changed to a gas, then all of the energy that's been inputted is being used to break the bonds in order for that material to change from a liquid to a gas. There is no change of temperature whilst the change of state is happening. And so if we look at that on a graph, it would look something like this. So we start off with a solid material, and as that solid is heated, then the temperature will start to rise until it gets to its melting point. And remember, melting point and freezing point are the same. So whilst it's actually melting, and at this point it would be partially solid and partially liquid, but during this time all of the temperature that is going into it, you can see the temperature doesn't rise. So all of the thermal energy that's going in is being used to weaken the bonds in order to change the state. Once all of the particles have become liquid, once everything is a liquid, then we start to see this change in temperature again, and the temperature starts to rise. The thermal energy is now being used to increase the average kinetic energy of the particles, and it is purely a liquid at this point. Once it gets to boiling point, again we have this temperature, this non-temperature change, so it stays at the same temperature. And at this point we have liquid and a gas happening. So we have both changes of state. It's during the change of state there's no change in the temperature. And all of the thermal energy that's been inputted into the liquid is being used to break the bonds in order to change it to a gas. If we continue to heat that gas, once all of the material is a gas, then again we'd see a rise in temperature. And the reverse is true when we cool a material down. So if we start with a gas, as we cool that gas down, the temperature will reduce until it gets to the point at which it changes from a gas to a liquid. At this point we have a gas and a liquid, but the temperature does not change. And what's happening here is the temperature is being released in order to reform those bonds. Once everything has become a liquid again, we get this temperature starts to cool down until we get to freezing point. And again at freezing point we have this mixture of liquid and solid whilst the material is changing state. And at this point the temperature does not change again. Temperature is being released, but that release of temperature is being created by the bonds being formed. So as the bonds form, temperature is released, but the actual temperature of the material does not change. And again, once we get to a solid and everything is in a solid, the whole of the material is a solid, then again we will have this reduction in temperature. Now, as we saw from the graph, there are two incidents of the change of state. The first one is from a solid to a liquid, and this is called the specific latent heat of fusion. When the material changes from a liquid to a gas, we have the specific latent heat of vaporization. And as you can see from the table here for water, you can see that the specific latent heat of fusion, which is the ice to the water, is a lot lower than the specific latent heat for water to steam. And we can see that it takes a lot more energy to break the bonds in order for the water to turn to steam than it does to weaken the bonds for the ice to turn to water. And the specific latent heat equation is very simply the specific latent heat of the material times by the mass, and that will give us the amount of energy it takes for 1 kilogram of that material to melt, and there's no change of temperature at this point. So a very simple exam question that they tend to use in foundation papers is they will give you the specific latent heat. In this case, they've given you the specific latent heat of fusion for water. They will then give you the mass of the water, and they'll often tell you the temperature. Now, 0 degrees just means it's at melting point. So all we need to do for this is times the mass by the specific latent heat of fusion for water. The one thing to watch out for here is that the mass needs to be changed into kilograms. And so 100 grams in kilograms would be 0.1 kilograms. So remember to divide that by 1,000. All you do then is put that into the equation, and you would get 34,000 joules of energy needed to melt 100 grams of ice. For those of you doing the foundation paper, this is the level at which you need to be able to use this equation. For those of you doing the higher paper, or those of you that want to have a real challenge, we're going to see how you can link the latent heat equation with the specific heat equation to answer GCSE questions at the higher level. So here's the way in which an exam question may ask you to link these two equations. So the first one is very straightforward. It's calculate the energy transferred from a glass of water to melt 100 grams of ice cubes at 0 degrees. Now again, remember to watch your units. You do need to change them into kilograms. And for that one, you're just going to need the latent heat of fusion for water, because this is melting point. The second question will ask you to calculate the total amount of energy transferred for 200 grams of ice cubes, a change to steam at 100 degrees C. So what we've got here is we've got two changes of state which you need to use the latent heat equation for, and then of course you've got that change in temperature as well, and for the change in temperature you'll need to use the specific heat capacity equation. I've given you all of the information that you'll need there in black, so if you fancy a real challenge, pause the video now, see how you can do this, and then I'll come back and show you how to go about tackling it. Okay, so the first equation was basically to look at, it was basically the specific latent heat equation. So we had 100 grams, and again we need to change those units, so it's 0.1 kilogram. And we simply times that by the latent heat of fusion. So 0.1 times 340,000 gives us 34,000 joules of energy to change that state. Now the second one was, again, we needed to look at both equations. So we had the first part, okay, so the first part of this equation was to change the state. So we have this change of state, and this one is from a solid to a liquid. So again, we're looking at the latent heat of fusion. We know that to be 340,000, and the mass we were given this time was 200 grams, which gives us 0.2 kilograms. So we times those two together, and that gives us 68,000 joules of energy to basically melt the ice. Once the ice is melted, we're then going to need to look at the change of temperature. And for this, we're going to use the specific heat capacity equation. So we know that the energy is going to equal the mass times the specific heat capacity of water times the change in temperature. So we know the mass was 0.2, and we're then going to times that by the specific heat capacity of water, which is 4,200, and the temperature changed from 0 to 100 degrees. So the change of temperature was 100. And that gives us the energy needed to change the temperature of 84,000 joules. So the next part of this is to change the state again. This time we're changing the state from the change of state is from a liquid to a solid. And we know that the latent heat of vaporization is a lot higher at 2,260,000 joules of energy. We times that by the mass again of 0.2, and this gives us an energy of 452,000 joules. So what we've got breaking this down is we've got 68,000 joules of energy. That's how much it's going to take to actually melt the ice. We then used the specific heat capacity equation, and this is the amount of energy, 84,000 joules of energy, that it's going to take in order for us to raise the temperature to 100 degrees. Then during the boiling point, as all the liquid changes to a solid, we use the latent heat of vaporization, and again times that by the mass. So that would be 452,000 joules of energy to change that liquid into steam. We add those three together and we come up with our final answer to the question, which is 604,000 joules of energy is the total amount of energy that it's going to take that ice to change its state twice and raise its temperature. Okay, how did you get on with that one? So that's really as hard as they could possibly make it in the higher paper for combining these two equations. So hopefully you now have an understanding of what's meant by latent heat. You're able to realise that when a material changes state, that the temperature doesn't change, and that any heat that's put into it is used in order to weaken or break in the bonds. You should now also have an understanding of how to do the specific latent heat equation, but also how to combine that with the specific heat capacity equation for those really challenging GCSE questions.